and welcome to this unpracticed presentation on DOD functions. Let's get started. The delta offset derivative function, otherwise DODs, set out to answer this question here. What if the derivative of a function was the same as the translation? Well, let's find out. First, let's think about some examples. One really famous example is the exponential function, f of x equals e to dx. By taking the derivative of the exponential function, we just get the exponential function. If any of you have taken a calculus class, you would know this. This is very primary in your knowledge. This x is the same as x plus 0. This function here shows that by taking the derivative, we have a translation of 0. So we have delta equal to 0. What about some other examples that we can think of? Well, what others but the sinusoids? What if we have f(x) equal to sine x or cosine x? Let's start by taking the derivative of sine x, gives us cosine. But then cosine is not sine. So how do we revert back to sine? Well, by getting a little bit into trigonometry, we know that the cosine of x is nothing but the sine of x plus pi over 2. By this meaning, we found the form x plus pi over 2. So our function has translated by pi over 2. Indeed, we can do the same with cosine. Deriving the cosine gets us a negative sign, which is indeed the pi half translation of cosine, retrieving this pi half translation delta value. So how are these two connected? On the one hand, we have an exponential function, and the other we have the sinusoids. They don't seem very the same, if you would. One is tending off to infinity as the others go and oscillate throughout infinity. Well, that comes from the famous Euler identity, or rather, the functional form. And it states if we take the power of an exponential of I times some argument, then we will get a real part and an imaginary part. The real part being the cosine of that argument, and the imaginary part being the sine of that argument. So what if we take the derivative of this? Well, if we get the derivative of e to the ix, we can separate it out by this identity to be cosine plus I sine. Then by the linearity of the differential operator, we can parse that out into cosine, or the derivative of cosine and the derivative of I sine. Deriving both, we get negative sine from cosine and plus I cosine from I sine. Doing over with the trigonometric identities, we get negative sine is cosine plus pi over 2, and cosine is sine of x plus pi over 2. Then we have this form, cosine of an argument plus I sine of an argument, which allows us to bring back up into the exponential form, which indeed retrieves our delta value, our translation of pi over 2. Great. What are we looking for then? If for delta equal to 0, we have f of x equal e to the x, and delta equal pi over 2, we have f of x equal e to the ix. Well, this kind of encourages us to look for a form where it has f of x is equal to e to the something times x. So let's just have that as that function, f of x equal e to the k delta of x, where we're setting this k to be another set of function that describes this constant that we're multiplying by x as dependent on delta. So we know for our 0 value of delta, our k needs to be 1 to match with e to the x, and our k pi over 2 value must be I. What function can give us this? Well, that's also e to the ix. For e to the I times 0 is e to the 0, 1. And as well, e to the I pi over 2, if we go back and think about the relation, the Euler's relation, that is cosine of pi over 2 plus I sine pi over 2. Cosine pi over 2 is 0, and sine pi over 2 is 1. So you get 1 unit of the imaginary. So we can try that value. Try k of delta is equal to e to I. Plugging that in to our f of x, we have e to the I delta times x. Taking the derivative and plugging it in, we have that e to the I delta is a constant relative to x. So by the, not the power rule, sorry, by the exponential rules that come with e, we can just bring it out front as a constant. And as the two powers are the same, we have e to I delta and e to that function. They can be brought in as an addition of the two powers. So it's e to the I delta times x plus I delta. Now we're trying to retrieve this form of e to the I delta times x plus the translation. So in order to do that, we can try to bring in this e to the I delta. However, we have to introduce the inverse as well in order to put it in with I delta. So by doing so, we have e to the I delta times x plus I delta e to the minus I delta, where e to the minus I delta is that factor, that inverse factor that cancels out that e to the I delta. So now we have this form of x plus some other value. But that shows that we have to have, this has to satisfy that delta equal to I delta e to the minus I delta. However, this is not true for all delta. So this fails. However, it did come with some interesting forms. When we saw this value of k delta equal e to the I delta, its constant value brought down that e, and that e power allowed us to just add that function, that power function. So let's try to go with that. Just trying a general function in that power now. We plug that in, of f of x equal e to the capital F delta, where I'm just using the capital to denote that it's different from the small f of x that we're trying to use here. Taking the derivative, again, that e to the f of delta is completely independent of x, so it comes down as a constant, and then we can add the two exponents. Now, again, to get that, we want a value of x plus something to be multiplied by e to the f delta. So we just multiply by the inverse in order to bring it inside. Now we can have this value. We have x plus something here. All we have to do is solve for that something to be equal to the delta. So in order to do that, we need some tools. One really useful tool is something called the Lambert W function. The Lambert W function is described as the inverse of this other function, where f of x here is just being used erroneously just because it's a function. So if we have a function of x equal e to x e to dx, then the inverse of that function is the Lambert W function, where we get then that the Lambert W of x e to dx equal to x. So how does that give us anything? Well, if we negate our function that we have here, we have negative delta equal negative f delta e to the negative f delta. So we see we have this form, negative f delta e to the negative f delta. If we take the Lambert W function, then we just kind of altogether ignore all that craziness, and we get just negative f delta out of it. And this is nice. All we have to do is now remove that negative. So taking the negative, we find that f of delta is equal to negative the Lambert W function and negative delta. Great. So we have that. We can actually put it into the solution. Our function we first found was kind of looking like it had e to the k something, k of delta times x. Then we found that k of delta to be itself a power of e of exponential e to f of delta. And then we found that f of delta to be the negative Lambert W function of negative delta. So we have our form, finally. Why do we care? Well, let's think about fractional derivatives. The derivative operator, when we take a derivative of a function, is usually denoted by these hash marks or primes, however you want to call them. If we want to do the derivative of that f prime, that already derived function, then we're taking the derivative of the function. That derivative can stack, and we denote it with a 2 over for d squared over dx squared. And this is also often denoted with a double hash, double prime, whatever you want to call it. And again, trying to take the derivative of that is just taking the derivative of the double derivative, which brings up this 3 power, this d3 by dx3 of f of x, also given the triple hash. When we're talking about fractional derivatives, though, we're talking about any n. So this n could be 1/2. It could be 1 pi. It could be anything. We just want to figure out what this value could be. Now, it does have some solutions, and those solutions involve taking in the Taylor series of a function and using fractional factorials. But fractional factorials and taking infinite series, that can look a little bit messy, and it's not always helpful. The simplicity of dot functions comes in. We take the derivative of the dot functions. By definition, it is a translation. So deriving d by dx of f of x will just give you f of x plus delta. If we then try to take the double derivative, that is the derivative of the derivative, then we're just taking the derivative of this translation, which just translates it again. Again, if we try to take the triple derivative, it's just the derivative of the double derivative, which is the derivative of f of x plus the second translation, which is a third translation of this 3 delta value. So when we take the fractional derivatives of DODs, while this is not so much of a proof as much as it is anecdotal evidence, we have that d to the power of n over dx to the n for whatever n of these functions is just this translational separation of n times delta. The marvelous fact about this is that it works for any and all n and delta. Of course, this isn't a proof video, but it does kind of show you a little bit that it can be used for so much more. This isn't necessarily for even rationals or reals. It can be in complex numbers as well. So wonderful. There is an alternative solution to this, just a little bit. If we start with e to the kx being our function that we wanted, we can take the derivative, take that log, or take the k into power by being a log, separate out that k, then get out this delta equal log k over k, then go through the processes to solve for k, which gives us this form, negative Lambert W of negative delta over delta. This is a little bit different from what we had, but it is indeed the same as this e to the minus Lambert W of minus delta by its own sort of work. Now, this can become a little bit more intuitive if you have that sort of intuition, but I like the journey of the logic of the latter, or the former. Yep, this was on practice.